The strength of those forces holding the particles together depends on the structure of the forces, and the state of matter depends on the strength of the intermolecular forces. So if we have strong forces, if the particles are held tightly together, that means we have to get to a higher temperature to melt that substance or to boil it. So strong forces give us high melting and boiling points. If we have weak forces, it doesn't take much energy to get those guys moving enough to break loose from each other, so we have low melting and boiling points. These intermolecular forces arise from charges, the interaction between charges. Some of these are partial charges, some of them are temporary, and they are all small charges. So here's Coulomb's law again. So the potential energy of two oppositely charged particles is going to depend on the charge and the distance between them. So the greater the charge, the greater the attraction. If the distance between them gets smaller, then the attraction will be greater. So when we look at bonding forces, which we just spent several chapters talking about, what we're looking at there is we're looking at large charges at very close distances. So the bond between oxygen and water and hydrogen and water is like 96 picometers, whereas for the intermolecular forces, we're looking at a distance more of 300 picometers, 3 times as large. And on top of that, the charges are smaller. So the intermolecular forces are much weaker than the bonds. So let's talk about the different types of forces. So the weakest one is called a dispersion force. It's also called a London force, or sometimes a London dispersion force, or an induced dipole force. These types of forces are present in all molecules and all atoms. And these come about because of fluctuations in electron density. So here we have a helium atom, right? We have 2 electrons, and there's the nucleus. And so if we took pictures of these electrons, forcing them to behave as a particle, so we can take a picture of them, and we took pictures of them, we would see that occasionally both of those electrons are on the same side of the molecule. And when they're both on the same side, that side of the atom, sorry, not the molecule, the atom, but that side of the atom is going to have a partial negative charge, and the other side of the atom is going to have a partial positive charge. It's going to be lopsided. It won't stay that way. On average, the electrons are evenly distributed around the nucleus, but the average includes lopsided on both sides, right? Does that make sense? Yeah, my iPad's doing something funny. So we call that lopsidedness an instantaneous dipole, or a temporary dipole. So here we've drawn it a little more lopsided. So here's the 2 electrons over here. They just happen to be over there. And so this end is partially negative and this end is partially positive. So when a neighboring helium atom is in proximity to this, the positive side of this atom attracts the electrons in this helium and causes or induces a dipole in this one. And we have this attraction between the temporary dipole in each of these atoms. This temporary dipole in this one is going to cause a temporary dipole in the neighbor. So I think of this a little bit like, I don't know if you've ever been to the San Francisco Bay, and there's Alcatraz out there, and there are these ships that you can pay like way too much money to go on a cruise, right? And they drive you out and around Alcatraz and back. And so you can imagine, you've got people on both sides of the boat, right? And they're looking around, But as you get close to Alcatraz, everybody's going to go to the same side because everybody wants to see Alcatraz, right? So everybody's going to go to the side, and that's going to cause the boat to tip to one side just a little bit, because hopefully they're following the rules and they didn't overload the boat, right? But it's going to cause it to list just a little bit. And so that tipping of the boat might induce another boat to tip a little bit because everybody's looking to see if that boat's going to tip over. I don't know. So the magnitude of this, how strong it is, depends on how easy it is for those electrons to move or become polarized in response to an instantaneous dipole. So we think about this, a larger electron cloud is easier to polarize because the electrons are held less tightly by the nucleus. So if you can imagine like xenon's a big atom, right? Its electrons are out in the fifth? Xenon, yeah. N equals 5 principal quantum level, right? They're way out here, far from the nucleus. And so they're just like in the perimeter here. It's easy for those to get more lopsided than for a small atom like helium, where the electrons are in the first principal energy level. They're very tight and close in to the nucleus. So these electrons don't get lopsided as easily as a bigger atom does. Does that make sense? Because these are more easily polarized, then the response to an instantaneous dipole is greater, and this attraction between these atoms is greater. And we can see evidence of that in the boiling point. So these are boiling points in Kelvin. So helium has a boiling point of 4.2 kelvins. Crazy, crazy cold. And as we go down these noble gases, we see that the boiling point increases, which tells us that the strength of the forces attracting them. Did I say go down? Did I say up? Okay. I just like my brain the train just jumped the track. Don't know where it goes. Don't know where it goes. Okay, reset. As we look at larger and larger atoms, the boiling point increases because the electrons are more floppy, right? They're more polarizable, and so you get an instantaneous dipole in one, and the next one is easier to become lopsided and become attracted. And so the force of attraction between xenon atoms is larger than in helium atoms, and we see evidence of that from the higher boiling point. So dispersion forces generally increase with molar mass. The shape of a molecule also plays a part. So here we have two different forms of pentane. This is normal pentane, and this is neopentane. So they have the same number of carbon atoms and hydrogen atoms, the same molar mass, 72.15. They have the same chemical formula. The shape of the molecule is different. So these are space-filling molecules. These are sort of shaped like pills, capsules, right? They're oblong, and these are going to be spherical. And so if we think about this kind of long and skinny molecule, there's more area where it can interact with a neighboring molecule, because it has to be close in order to have a significant attraction. So here we can have more of each molecule be close to the other molecule, whereas with the spheres, there's only a small point that can interact. So if you think about these two shapes being covered in Velcro, and these two shapes being covered in Velcro, these are not going to stick together very well, right? Two balls, because they just touch at one little tiny point. Whereas here, you've got a larger surface area, right? So I don't know if any of you guys had Velcro shoes when you were kids, or maybe you still do. Sometimes that Velcro kind of wears out and you're like, yeah, Velcro's not all that strong, right? And it's easy to tear it off. And yet if you get in one of those Velcro suits at one of those bounce house places and you jump, you bounce and bounce and you jump against the Velcro wall, have you seen that? I've never done that. I need to find a video of that. You're going to stick, right? Because it's your body. You stick because it's a large area, right? Whereas if you just had like one Velcro covered finger out, that's not going to hold your body up on the wall because there's not enough area. So here we have very little area where they can stick to each other. Here we have more area. So this is going to have a higher boiling point because the intermolecular forces are stronger. And we see that this has a boiling point of 36, and this has a boiling point of 9.5 degrees Celsius. And the only thing that's different is the shape of the molecule. So we can use molar mass when we're comparing similar elements or compounds. So we can compare like the noble gases and say, well, xenon is bigger and it has stronger intermolecular forces. But we can't compare a noble gas atom to like a metal atom because they're very different. Right? Here's a comparison of some alkanes. Remember, alkanes are also called hydrocarbons. They just got carbons and hydrogens, and they're all single bonds. So these are all what are called straight chain or normal alkanes. And so the carbons are in a row, and the hydrogens are around them. So as we go up in molar mass, because we're getting more carbons and more hydrogens, we see that the boiling point also increases because nonane has a greater surface area that those molecules can be attracted to than pentane does. Okay, so that's the effective shape again. So these are the kinds of questions we should be able to answer. Which halogen has the highest boiling point? So these are the halogens, chlorine, bromine, iodine, they're in the same group in the periodic table, the same column, right? So high boiling point, is that going to be strong attraction or weak attraction? Strong attraction. So this obviously is based on size. We've only talked about dispersion forces. So which one of these is biggest? Iodine, because we know that as we go down a column, they get bigger. So chlorine is smaller, and bromine is bigger, and iodine is the biggest. So iodine has the higher boiling point. And you can actually look at the states at room temperature and see that. Because chlorine is a gas at room temperature, bromine's a liquid at room temperature, and iodine is a solid at room temperature. Second kind of force is called the dipole-dipole force. This is going to be stronger than dispersion forces because these are dipoles that exist all the time. They're not temporary. In the dispersion forces, we have a dipole form and then go away, and form and go away, and it would cause dipoles in the neighboring molecule, but they just came and went all the time. Here, the dipoles are permanent. They're always present, and so we're going to have stronger attractions. And we're going to see this in polar molecules. And this is part of why we had to learn how to identify what's a polar molecule. Okay? So here, this is a space-filling model, and here's the electrostatic potential map. We've got a negative end and a positive end. We've got the delta negative and the delta positive. The positive end of the dipole on this molecule is attracted to the negative end of the dipole on the neighboring molecule. Polar molecules also have dipole-dipole forces, which I would encourage you just not to think about that too hard. Everything has dispersion forces. Polar molecules have dipole-dipole forces on top of that. And because of that, the polar molecules are going to have higher melting and boiling points than nonpolar molecules of the same size. So here we're comparing comparing formaldehyde and ethane. Molar mass is almost identical. And here we see Lewis, well, kind of Lewis structures. Here we have carbon and hydrogen bonds only. Carbon-carbon, carbon-hydrogen, those are all non-polar bonds. So this compound has to be non-polar. Here we have no lone pairs on the central atom, but one of the atoms is oxygen and the other two are hydrogen. This molecule is lopsided. It's going to be polar. And if we look at the boiling points, formaldehyde boils at -19 and ethane boils at -88. So this boils at a much lower temperature, telling us that those intermolecular forces are much weaker. You follow that? Here's comparing the dipole moment, how strong the dipole is in these molecules, looking at the effect of that on the boiling point. And notice that the molar masses of these guys are very similar. So you can't compare them if their molar masses are significantly different. So we see that as this dipole moment increases, so does the boiling point. Another thing that intermolecular forces are important for is determining whether things will mix. So this word miscibility, kind of a funny word. You could kind of think of it as mixability. Will those two liquids mix together? They are miscible if they will mix together. The way to remember this is this little phrase, like dissolves like. If we have two polar compounds, they are probably mixable. They will probably mix with each other. If we have two nonpolar substances, they will probably mix together. But if we have different ones, they're not going to mix. And here we have pentane and water. Pentane is all carbons and hydrogens, completely nonpolar. Water is very polar. And so the water molecules are attracted to each other very strongly, and they push the pentane molecules out. So if the polarity is similar, then they will likely mix together. This is another good exam type question. Which molecules have dipole-dipole forces? So what are we looking for? Polar molecules, right? So we're trying to identify if any of these are polar. If they're polar, they're going to have dipole-dipole forces. So, the way to do that is to look at Lewis structures. And here I gave the name because I didn't want that to be confused with something ridiculous, Cl4. So this is carbon tetraiodide. So we've got 4 iodines attached to the carbon. Are there going to be any lone pairs on that carbon? No, because carbon can't expand its octet. It can only have 8 electrons around it, and here with the 4 bonds, it's got those already. If we finish out the Lewis structure, we'll find that there's lone pairs on the iodines. But here is where you can use those shortcut rules. So we look at this and we ask ourselves, are there any lone pairs on the central atom? No. Okay, that's condition 1. Are all of these atoms the same? Yes, that's condition 2. This is symmetrical. So even though the carbon-iodine bond is polar, because it's symmetrically shaped, as they're pulling on each other, they cancel each other out. So that means that this is nonpolar. Does it have dipole-dipole forces? No. Okay, CH3Cl. Yeah, that one's going to be polar. So here we've got carbon, no lone pairs. Carbon never has lone pairs. But the chlorine is different than the hydrogens. It has a different electronegativity. So the dipoles here, well, those are actually not dipoles. There's going to be an overall dipole here. This is going to be lopsided. So that one's polar. Does it have dipole-dipole forces? Yes. All polar molecules have dipole-dipole forces. How about HCl? Yeah. HCl, we just got one bond. We have two atoms, one bond. If the bond is polar, the molecule's polar. And what I want you to be able to recognize is if those are two different nonmetals, you should say it's polar. That's not absolutely always true, but it's true most of the time, and it's much easier to remember. So that's also polar. So any questions? Yes?
That doesn't work with ionic bonds?
Well, so ionic bonds aren't molecules. Ionic compounds don't have molecules, so they don't have intermolecular forces. Well, we'll talk about what they do. They do have interactions with water, the ions do. And that's in this chapter, but it's not technically an intermolecular force.
Okay.
So here we're talking about molecular compounds only.
Okay.
Mm-hmm. So here they're showing us electrostatic potential map for acetonitrile, CH3CN. It's polar. And so we see here this nitrogen end is negative and this carbon-hydrogen end is positive. And it's asking us, from this map, determine how two of these molecules would interact with each other. Which of these types of interactions is most likely? So this is the nitrogen. This end is going to be a little bit negative, and this end's going to be a little bit positive. So are we going to have the attraction between two positives and two negatives? Or between opposite charges? Opposite charges. So which of those do you think is most likely? I heard a vote for A. Anybody else? So here we have the nitrogen end and the nitrogen end. So we got the nitrogen and the carbon end close to each other. This is the negative end and the positive end. Here, the nitrogen ends are negative and they're kind of next to each other, kind of overlapping a little bit. Here we've got one going this way and one going that way. And here we have both nitrogen ends together. So the answer is A. The oppositely charged ends will attract each other. Any questions? A third type of intermolecular force is hydrogen bonding. And I like to think of this as super dipole-dipole force. It really is a dipole-dipole force. It's an attraction between dipoles. But it's extra, it's super, it's a lot stronger. So this will be found in polar molecules, but ones that contain hydrogen bonded to fluorine, oxygen, or nitrogen. These are small and very electronegative elements. So this is going to be a stronger attraction than a regular dipole-dipole force because the partial charges are fairly large, because these are highly electronegative and this is not very electronegative. And we also have small atoms, and so they can get close to each other. So we get higher Qs and smaller Rs, and this is going to be extra strong. This is one of my favorites. So how do you remember that? heard of the movie E.T.? And what did E.T. do? What did he want to do? Phone home. Right? Phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. Here we can look at hydrogen bonding in ethanol and in water. So here we have oxygen bonded to hydrogen. Oxygen bonded to hydrogen. And so the dipole here is especially strong. These atoms are small and they can get close together, and so we get an attraction between the hydrogen and the oxygen here. Here we have water. Water has two hydrogen-oxygen bonds. Again, the partial charges here are large and the atoms are small, so they can get close together. And so it's the dotted lines here that represent the hydrogen bond. A hydrogen bond is not a covalent bond. It's an attraction between two molecules. Hydrogen bonds are between molecules. Chemical bonds are within a molecule. The hydrogen bonds are only like 2 to 5% as strong as a covalent bond. But what we see is that compounds that have hydrogen bonding, so compounds with hydrogen bonding, here we have ethanol. We got this oxygen-hydrogen bond here. Dimethyl ether, same chemical formula. This is, well, kind of polar. It is a little bit polar, but the oxygen here is bonded to carbons. It's not bonded to any hydrogen, so there's no hydrogen bonding. So if we look at the boiling point, ethanol boils at 78 degrees Celsius, and dimethyl ether boils at minus 22. It's a huge change. Same size. Dispersion forces are the same, but the hydrogen bonding makes a huge difference. The hydrogen bonding in water makes it a very unusual compound. This graph is showing us the boiling point versus molar mass for some hydrides. So these are the compounds, hydrogen with oxygen, sulfur, selenium, and tellurium. So these guys are in group 6A. These guys are in group 4A, carbon, silicon, germanium, and tin. And there's a bit of a trend here. I don't know why I'm stuck on orange today, but that's kind of linear, isn't it? Oh, that wasn't good. My hand slipped. That's kind of making a line, those three. This is a nice trend, right? As the molar mass gets bigger, the boiling point gets higher, dispersion forces are stronger, right? Why is water way up here? We would expect it to be down here somewhere. It has such a high boiling point because of the hydrogen bonding that holds it together. And with these guys, what we see is that the methane goes with a much lower boiling point because it's very nonpolar. So if water didn't have hydrogen bonding, all the water on our planet would be in the gas state. That wouldn't work out for being alive, would it? There's an awful lot of water in your body. Which has the higher boiling point, HF or HCl? HF. Why? Well, it's not that F is smaller. It has to do with ET. So both of these are polar molecules, right? And if it was just based on size, we would expect HCl to have a higher boiling point because the dispersion forces are larger. But we have fluorine-hydrogen bond. And so this compound has hydrogen bonding, and so it's going to have a higher boiling point. How many more do we have here? So the last force is called the ion dipole force, and it's not really an intermolecular force. The intermolecular forces are between molecules, and they can be between molecules of the same substance, so within water itself. Here you have to have a mixture of some kind. So this is when you have an ionic compound mixed with a polar compound. And we'll usually see this with water. So we've looked at a lot of different aqueous solutions, things dissolved in water. And these solutions can happen because of this ion dipole force. So this is stronger than hydrogen bonding, and it's why you can dissolve ionic substances in solutions. So what happens here is the chloride ion, the negative ion, it will attract the positive ends of the water molecules. And so they'll kind of rally around it, come around and make it feel comfortable, and kind of take it off into the rest of the water and swimming away. And here we have the positive ion, and the negative ends of the water molecules are attracted to that. And so it's kind of a creepy analogy, but here you've got sodium chloride, and it's a solid, and they're all together, right? They're attracted to each other. And then you have water that comes in and lures chlorine away, and it lures sodium away, and they get separated. Let me know if you come up with anything better. This is a table just showing different types of intermolecular forces, what they're present in, and their relative strengths. Okay, which of these substances has the highest boiling point? I've got a vote for C and a vote for A. So what we want to look at is what kind of intermolecular forces do they have? So dispersion forces are the weakest, right? And then we get the dipole-dipole forces. And then we get the hydrogen bonds. Everything has dispersion forces. So all of these guys have dispersion forces. If they only had dispersion forces, we would use their size to compare them. But they have different things going on here. So we're going to look at the different kinds of forces first. What kind of molecules have dipole-dipole forces? Polar. Is N2 polar? No. So this one just has dispersion forces. We call it DISP. And both of these are polar. So these have, everybody's got dispersion forces. And then these guys also have dipole-dipole. I have DISP and dip-dip. Can either of these form hydrogen bonding? A, because we have an oxygen-hydrogen bond. So this also has hydrogen bonding. Hydrogen bonding is the strongest of the intermolecular forces. Strong forces, higher boiling point. Okay? Oops. Yeah.
So hydrogen bonding can happen within the molecule itself, then also between other molecules, or no?
Hydrogen bonding does not happen within the molecule. There is a hydrogen bonded to oxygen, but that's a covalent bond. Okay? The name is very confusing.
So in that one, like the oxygen is exposed enough to the okay. So then what was that situation where you showed earlier where it was like the same exact formula, but one had the oxygen on the outside or something like that? Or
Yeah, one of them had the oxygen on the inside. It was still polar because there's lone pairs on that oxygen, and that would be the central atom. right? But it can't do hydrogen bonding because the oxygen wasn't bonded to the hydrogen. It was bonded to carbons.
Okay.
So that one was this guy. Versus this guy.
But so what's to stop the? Because I thought it was just the interaction of oxygen with either H, or either with like H, F, or N, if they're present in the solution.
So it's you have to have in the molecule hydrogen covalently bonded to fluorine, oxygen, or nitrogen.
Oh.
So here we have oxygen, it's a polar molecule, we have hydrogens. But here the oxygen is not bonded to the hydrogen, it's bonded to carbon. And so the dipole here is not as strong. Over here, we have the oxygen and hydrogen bonded to each other. And so that's going to be a stronger dipole, bigger separation of charges. And we can predict the shape here. That's going to have a bent shape, right? And so that oxygen is kind of sticking out. And so another molecule of this could get close to it and be attracted. Yeah. And, oops. The one we were talking about here, this is methanol, this guy. So this is an oxygen-hydrogen bond. It's a covalent bond. We talked about covalent bonds. The hydrogen bond occurs when you have another, I keep doing that, when you have another molecule where here, because we've got this dipole, and so this is a little bit positive, that's a little bit negative, and so we have this attraction between the molecules. Now these, this is ethanol, that's methanol. Both of those are miscible in water. They mix with water very well because water also has hydrogen bonding. And so it's like they talk the same language and they just mix and mingle and they get along so nicely together. Any other questions? And this is just a little bit of why should we care about hydrogen bonding? Hydrogen bonding holds your DNA together. That's kind of important. So, if you didn't know, your DNA is composed of 2 long strands, right? And it can replicate, these strands get separated, and then a new corresponding strand is made on the old strand, and so you go from having 1 DNA strand to having 2 of them, and they are identical. And the reason here is that we've got these different bases. Thymine and adenine can make 2 hydrogen bonds with each other. Cytosine and guanine can make 3 hydrogen bonds with each other. So we'll always see C and G matching up, A and T matching up. The T is never going to match up to G. An A is never going to match up to A because they don't fit together right. And so your body can make a new strand of DNA by matching up those base pairs using hydrogen bonding. Very cool.